quantum mechanics, 10 minutes of quantum mechanics. So from now on, there's no quantum mechanics. It's all classical. So this is something that we could have done in the 19th century. So they were already doing all the stuff I'm telling you, they were already doing in the 19th century. So the plan is to talk about the Bloch equation. So there's three parts of the Bloch equation, three terms. Terms are things, that have multiplication in them that are added together. So there's three terms of the Bloch equation, and we're just going to do the first term of the Bloch equation to try to understand how that works. But that involves some vector addition and, more importantly, vector multiplication. So we have to back up and talk about different ways to multiply vectors, because there's a cross product in that first term, and that's one way to multiply a vector, but you can there's several other ways. And while we're at it, we'll talk about complex numbers. How do you multiply complex numbers? How do you add and multiply complex numbers? Because we're going to need to do that later on too. And so it's helpful to sort of see them all in the same, like the dot product, the cross product, and the complex multiplication all in the same sort of format. So you can see that they're all slightly different. Okay, so let's write up the Bloch equation, the first term of the Bloch equation. So here it is. So it's that thing. Okay, so what is that thing? So that thing is how the m vector is going to change over a small amount of time. So what's the rate of change of the m vector over a small amount of time? That's got three numbers in it, because that thing is a vector itself. So this is how the m vector changes, but it's also a vector. And so what does that mean? So if we draw out a little coordinate system here, how do we, why does that thing have three numbers to it? So let's draw out an m vector. So here's an m vector sticking up like that. So that guy is an m, not a dm dt, an m. That also has three numbers. And so what are those three numbers? Those three numbers are, let's say it goes down something like this. So here's the three numbers. So there's the x, well, let's call this guy the z-axis, and here's the x-axis, and here's the y-axis. So here's the z right there, and then here's the y right there of this guy, and then here's the x. And so basically, let's make sure this guy goes in front of that one. Okay. So basically this, you can describe this thing, by x, y, and z. And it's what's a vector is just like it's an arrow pointing in some direction with a certain length. So what's that thing? So this thing is another vector, smaller vector, and that vector says how the m vector is going to change. What's the change in the m vector, which is a vector? And so what is that vector? That would be, put that in a different color. That guy is, say, like that. So that one is the change in the m vector over a short period of time. And what's that useful for? That's useful for telling us how the m vector, where the m vector is going to go next. So there's the m vector at one time point, and now we've got the vector that's the change in the m vector, and then that tells us, where the m vector is going to go in the next time point. So that's what the Bloch equation tells you. It says, like, how is the m vector going to change? That's what the meaning of that first one is. All jammed in there. It's got three numbers. in 3D. So that's good. And then there's only 3 more parts. So then what is this equal to? It's equal to the m vector cross-producted with this thing, with the b vector. And this guy is, that's just a constant gyromagnetic ratio. This guy is the field that's applied, so that would be like the superconducting magnets that make the B0 and the gradient coils, so that's the B0 plus gradient plus RF. RF is in there too, the magnetic field coming from the RF coil. It's all added in there. And then this thing is that thing that we said was the bulk magnetization. And what does that mean? That means, like, for a given voxel, what is the magnetization after you've added up all the quantum funny business at the low level? And we forget about the quantum business, just add it all up, and then we get that amount of and direction of magnetization in a little chunk. And that can be different in different voxels. So different voxels can have different amounts of magnetization, but we're not drilling down to the atoms. We just say, like, in that little chunk, this is what the magnetization is. And so that's the M. So this is bulk mag. Just almost off. Okay. It's bulk mag, and then this guy is down here, the change. Okay, so that's the picture. So we're trying to figure out, like, what the heck does that mean? What does this whole mess mean? And that tells us how to change the M vector. So now, before we multiply vectors, we have to sort of just remember quickly how to add vectors, because here we're adding vectors. And so how do you add vectors? That's you can think of it 2 different ways. And so one way is, say we have a vector, this vector A vector here, and we got another vector, say the B vector. So how do you add those? So the simplest conceptual way to think of this is you just take this guy and sort of like tack it onto the end of the, so just move this guy over here and tack it onto the end, and that will then give you the sum. So here's the sum, like that. So that's the C vector, which equals the A vector plus the B vector. So tip to tail. Now we're going to think of this as kind of more fiddly, but you can think of it in terms of the coordinates of that vector. You have to sort of establish some coordinate system. Here there's no coordinate system. It's just sort of sitting in empty space somewhere, and it's just like, it's just a vector. You don't have to sort of worry about where it is exactly. You just sort of stick it on the tip to tail. So let's just add those guys by coordinates. And so let's just do it in 2D to make it so we don't have to sort of mess with 3rd dimension. So if we have that one guy, so the one guy is, let's make it in different colors. So here's the first one, and then here's the second one. So how do we add those things? We just basically add the x coordinates to the x and the y coordinates to the y. So here's the two. So here's so this guy was B. B. This guy was A. So here's AX, and here's AY, and here's BX and BY. And so how do we add them? We just add the x's to the x's and the y's to the y's. And so basically the c vector just, equals the a vector plus the b vector. But how do we actually do it in coordinates? We just do it. The result is a matrix of numbers, except it's just got only one line. So this is a matrix of numbers, and all we do is just add ax plus bx. That's the first number in the matrix, and the second number in the matrix is ay plus by. And so then that's how we add. And so let's just do that up here. So you can see if we take, I messed up my ax. So if you take ax here and add it to bx is negative, and so that means the ax, and you come back a little bit. So there's cx. This guy is cx. And then what about the y? So the y is going over here, and then here's another y, so tack that one on top, and so we end up with this here, and that's cy. And so if we go to cy and cx, then we get, so we can do the same. So that's the same thing as tip to tail, except that we just did it with coordinates. Okay, so that's easy. And it turns out if you look at complex numbers, that's how you add complex numbers, same way. You can sort of think of complex numbers as a vector, two-dimensional vector, and how do you add them up? You just add the real parts, add the imaginary parts. That's just like this. Okay, so that was just adding. That's all. It got a little hairy with the 3D, but that's pretty reasonable. So now let's talk about multiplying vectors. So it turns out there's lots of different ways of multiplying vectors, and it's important to sort of keep them all distinct in our minds. And so the first way, which we haven't used yet, but we'll use in the next couple lectures, is the dot product. So that's one way to multiply vectors, the dot product. It's called a product. And so how does the dot product work? So let's start off with put it over here, little space, yeah. Dot product. So the dot product, there's several ways you can think of this, and there's several different names for it. So sometimes it's called the inner product. That's the same thing. Product. You can think of it as the scaled projection onto. Scaled projection onto. We'll explain that. You can think of it as the correlation. A dot product, that's how you calculate a correlation, is a dot product, basically. So what's the dot product? So the dot product it's a weird product because it takes two vectors and it kind of downgrades them. It downgrades them into a number. So here's that number. That thing C that you get from doing a dot product is just a number, not a vector anymore. So this operation kind of destroys the vector and just turns it into a number. So here's the A vector, and we usually use a dot, which, this problem with math, it can mean a lot of different things. It could mean like a dot product, or maybe it just means multiplication. A lot of times you just leave it out when you multiply, but usually they just write the dot product as a good solid dot, good solid dot, and then we multiply it by this thing, and we get a number. So this guy is this guy's a scalar, just a single number. This thing is a vector. It could be a vector of any dimension, like 2-dimension, 3-dimension, 20-dimension. So this works for any dimension. And so how would we write it out in coordinates? So the way you write it out in coordinates is basically, we could write it out as a matrix multiply. So I'll do that for all the cross product and complex multiplication, so you can sort of see the thing. So here we have we'll do it for 3 dimensions, but you could do it for more dimensions. So here's B x, by, bz. So those are the three coordinates of the b vector, and then we multiply by the three coordinates of the a vector, ax, ay, az. And the way you do matrix multiplication is you take a row of the matrix and you multiply each of the members of that row by each of the members of the column. So the bx gets multiplied by the ax, and the by gets multiplied by the ay, and the bz gets multiplied by the az. So, and then you add them up. So you multiply each of those guys and then add them up, and that's how you do the dot product. So it's basically, so if you just write that out, write out the matrix multiplication, it's going to be ax times, did I write? Yeah, all right. The order doesn't matter because you can flip the order for multiplication. You can also flip the order for a dot product. We'll come back to that. So it's just ax plus ax times bx plus ay times by plus az times bz. And you can think of that as a matrix. It's just a matrix with one number. So that's just a single number because they all got added up and you just ended up with one number. So when you do that matrix multiply, this kind of matrix multiply, you just end up with a single number. So that's how you calculate it. And so how you do just multiply the x's, multiply the y's, multiply the z's, add them up. So this one can go either way. It doesn't matter what order you do this in. You could sort of b dot a is the same as a dot b. Okay, but it turns out it also equals something to do with a cosine. So, and we'll talk about sines and cosines. Everything's all sort of stuck together. So here's the a vector. If we take the length of the a vector and multiply it by the length of the b vector, multiply that by the cosine of the angle between them, that's also a completely different way of getting this c value. So let's just draw the vectors out here. So here's a b vector. There's a b vector, and here's an a vector. There's the angle between them. So that's the a. Here's the b. So what does this look like? Well, if you take the cosine, what the cosine is going to tell you is basically if you project this vector down to here, we call that p. That's the projection of the a vector onto the b vector. Right angle projection. That's what you would, to calculate p, you would just basically put it in red. So how would you calculate p? You would just, p is just going to be equal to the length of a times the cosine of that angle, because it's the adjacent side. So that's the projection onto b, but it's scaled by b. So then we have to multiply by b, because we've now got to multiply by b, and so the final answer is the projection times the length of b. So that's what equals our c number. So that's why we said you can sort of think of a dot product as a scaled projection onto. Now if you set b to length 1, then everything's all good. You can just take the cosine. So if we project onto a vector of length 1, that will just give us the projection, just the cosine. It's kind of weird, like when you think about it, how does this multiplication, how do you end up with a cosine out of that? But that's the dot product. So we mentioned this sort of taking the length. We should mention how do you do that? How do you take the length of something? So what does that mean when we say take the length of something? Well, the way to calculate that is that's the square root of ax squared plus ay squared. That's the Euclidean distance, az squared. So if we square each of the components and take the square root of it, that's the distance. That's how you get the distance. So you notice that also is equal to the square root of the dot product of A with itself. So if we sort of if we do the this is exactly the same calculation here. We just multiply the A's times the A's and the B's times the A's times the A's, the AX's times the AX's, AY's times the AY's, and AZ's times the AZ's. So that's the definition of the Euclidean distance of a that's how you figure out the length of a vector. You square each of the coordinates and take the square root of that. Okay. And since this cosine here is here, we should sort of draw out the cosine. So, what does the cosine look like? So here's, if this is 0, 2 pi, 360 degrees, what does the cosine look like? It sort of looks like, let's put the marks there. So it starts at 1, and then it sort of goes down, and then it goes to -1, and then it goes to 0, and then back up to 1. So what does that mean in terms of how the dot product behaves? If the vectors are very similar in direction to each other, then that's going to be the largest dot product. And so that's why the dot product is a way of sort of calculating the correlation. So if you've got a bunch of things, how do you calculate the correlation? You basically take all their components and multiply them by each other and add up the whole mess. That's the same thing, essentially, as a correlation. So if the two vectors are very similar in direction, you get a big dot product. And notice it goes to 0, at 90 degrees at a right angle. So at a right angle, so if you take two vectors at a right angle, the dot product is 0. If you take two vectors that are parallel with each other but opposite, then you get a negative number. That would be like a negative correlation. Things, one's positive, the other one's negative. And then you go back up to 270, and you've got 0 again. And then when you go back to the same direction, you get a big dot product. So the dot product measures like how similar two vectors are to each other. Okay, so that's the dot product. And that works. It commutes, so you can, if you turn it around, B dot A is the same as A dot B. That's all good. So it's good so far. So now, draw a line here now. Oh, heck breaks loose, right? We got to do the cross product. Okay, so how does the cross product work? So the cross product is kind of a strange one. It only works. So physicists used to use different systems, but at the end of the 19th century, they kind of settled on the cross product. It's kind of a bit of a hack. Cross product's a bit of a hack, but it's a really useful hack. It only works in 3D. Doesn't work in 2D, doesn't work in 4D. And sometimes you need 4D or 20D if you're doing, like, say, a linear regression. But cross product only works in 3D. There's a way to generalize it, but we won't talk about that. So what is the cross product? Cross product is, it gives you a vector. So we usually write this as kind of like a big X, like a sort of an uncomfortably big X, so that you distinguish it from multiplication. So this time we get a vector out of it. And so what does it look like sort of geometrically? So if we've got, say, here's vector A and here's vector B. That's a vector A and vector B. The cross product result basically sort of comes out at you like that. So that's our C. So when we calculate the cross product, we end up with another vector that's perpendicular to both of them. And so what does that mean? So it's perpendicular to this guy. It's also perpendicular to that guy. So what does that also mean? It means it's perpendicular to the plane. Like whatever so if you take two vectors, A and B, that defines a plane. And so the C vector is going to be perpendicular to that plane with a certain length. We have to figure out what the length is. And so the cross product, if we write it out as a matrix, is kind of more of a mess. So here's a matrix with 0 down the diagonal, and I can't remember. I've programmed this many a time, but to this day I can't remember the exact entry of all these things. So I don't expect you to. So negative bx, and here's b. It should be z, shouldn't it? No, it's like b. Sorry, that's a bz. Yeah. There, there's bx. We got negative bx and by. So there's our matrix, and we're multiplying that matrix times our a vector. So here's ax, bx, sorry, ax, ay, b, az. Okay, so how do we do that multiplication? So that's going to be, 0 times ax plus bz times ay plus minus by times az. So what does the cross product look like when we, and so we're going to get, so that's the first multiplication, which gives us one number, which is going to be the x component of the output. And then the second multiplication will be this row times those guys again, added up. And that will be the second number, the y component, and then this last one will be the z component. But let's just look at how this works. So it kind of mixes the components. So it's ay times bz minus az times by, comma. And so you mix the y's and z's, and that gives you the x component of the output. And then you mix the z's and the x's. So now we have this is why you can see that I can't have to. So az, because I'm not a mathematician, I can't remember this, bx. So we mix the z's and x's minus ax b z, and that gives us, so when we mix the x's, that gives us the y component of the c vector, and then finally when we mix the x's and y's, we get the z component. So here's ax by minus ay bx. So looked at, by components is kind of a hairy mess, but the end result is we end up with a vector that's perpendicular to these, it's perfectly perpendicular to these two. And so what does this one, look like? What does the sign look like? It turns out this one is actually related to the sign. So everything's all tied together. So if we take the length of the c vector, so this guy's a vector, so we can't, this thing right here is just a number, because that's the length of a times the length of b times cosine, that's a number. If we just look at the length of the c vector, just ignoring its direction, that's going to be equal to, it's going to be a similar thing here. It's the length of the a times the length of the b times the sine of the angle between them. So there's the angle between them. So how does this one work? Well, if the vectors are perpendicular to each other, then that would be 90 degrees, and that would be the largest cross product. And if the vectors get parallel to each other, like 0 degrees, that would be a zero cross product. So it depends on sort of like the spacing and so you can see it's related to the area. It's a different kind of thing. It's related to the area that the vectors kind of sweep out. So one way of, so what does this cross product do? It actually tells you if you've got a vector like this, you have another vector like this, if we took that second vector and kind of swept it along the first one, that's actually what the cross product tells you. It tells you the actual area of that parallelogram. And so it's a different kind of thing than the dot product. Even though the cross product, just as a vector, you had two vectors and you made another vector out of it, it's really more like a two-dimensional thing. It's more like you kind of upgraded it from a vector to like a little sort of surface area. So that's the way you should think of a cross product. It's kind of like, it's something about a plane. It sort of defines kind of a plane and with a certain amount of area. And you can see, like, if you're how do you get the biggest area? Well, you make the vectors perpendicular to each other. How do you get the smallest area? You make them parallel, and then there's no area. So that's the cross product. So this guy is any d, so any dimension, and it commutes because you can do it back and forth. This one is 3D only, and it doesn't commute. So if you flip it, it changes the sign. So they call that anti-commutes. I won't work through it, but if you just flip B and A, what happens is you end up with a C in the same direction, but it's pointing the opposite. Say you end up with C in that's you end up with an output that's parallel to C, but it's pointing in the opposite direction. That's what the anti. So you have to. So that's kind of a pain in the butt because you've got to keep track of what. So if we flip this here, it wouldn't be the same. So it's not like a regular multiplication where you can just flip it and it's the same. Okay, so that's the cross product. So if you're interested in math, there's a cool, this was invented at the end of the 19th century. There's a cool method of doing three-dimensional complex numbers, or sort of cross-product-like numbers. Let me just put that off until we talk about the complex numbers down here. Okay, so that was the dot product, which was like a correlation, and the cross product, which is like kind of like an area, sort of defines a plane with some kind of area. It's kind of like an upgrade, really. This one is a downgrade to just two vectors made a number. Here we got two vectors, we kind of made a plane. But we got another third thing, which is complex multiplication. And so complex multiplication is yet a different thing. Which is different than both of these. And so what is complex multiplication? You can think of it as a vector multiplication that gives you another vector. And so what is what does kind of a little matrix representation look like? So in here we just have a 2 by 2 matrix because it's just a two-dimensional vector. by minus bx bx. Okay, and then times ax, ay. So that's the little matrix that we need to multiply complex numbers. And what does that look like geometrically? So what that looks like geometrically is yet something different. So it's only 2D. So this is basically 2D only. Although we'll show how to you can generalize it to 3D or other D. But what does this look like? So So this looks like we got one vector here, so that's one complex number, and you can think of that as basically it's got a real part and an imaginary part. The x, the real part is the x, and the imaginary part is the y. And then we've got another complex number. Say this is this other complex number, and that guy is b. So what is the geometrical picture of multiplying complex numbers? Because we're going to be doing this later on. And the geometrical picture of multiplying complex numbers is you multiply their lengths and you add their angles. So that's one geometric, it's easy to remember way of multiplying complex numbers. So here's this angle, and then here's this angle. So when we multiply complex numbers, we just add those two angles, and we get a vector in this direction, and so that's the c vector. This is our output, and the length of it is just equal to the length of A times the length of B. So what is, if we just write out how to do complex multiplication by the coordinates, the x and y coordinates of the complex number, you get something that's sort of like a cross product, but it's slightly different. So it's a. So you mix the x's in the first part minus the y's. So mix the x's and mix the y's, and that gives you the x component, or the real part of the complex number. That's the first number of the vector, of that output vector c. And then you mix for the second part of the number, you mix the x's and the y's. That's kind of like the cross product. But there's a plus here instead of all these guys are minus. See, all these guys are minus. This one has like a minus and a plus. And here's a, y, bx. So if you did this calculation, it would do the same thing as this. Yeah?
Is the matrix of bx supposed to be negative dy? Are we multiplying them?
Oh, did I? It should. Oh, yeah. This should be by. Yeah, sorry. Thanks. Yeah. There's y there and x there. Yeah. Sorry. Thank you. Okay. So that's so this is how you calculate the y component of the imaginary the y component of the complex number, which is called the imaginary component. It's not imaginary. It's perfectly non-imaginary. Okay. And so what does that look like compared in this final panel here, where we take the length of the vectors? Well, the length of the c vector is just equal to the length of the a vector times the length of the b vector, and the angle doesn't matter. So there's no sine or cosine there, so the angle doesn't matter. Angle is irrelevant. All you do is just add the angles of them, and it doesn't matter what angle they are relative to each other. So you can see it's yet a different thing, the complex multiply. Now, if you like these things, you probably don't, but if you like these things, so this basically only works in 2D only. But unlike the cross product, it commutes, so it doesn't. So when you multiply complex number A times complex number B, that's the same as complex number B times complex number A. So it's not whereas the cross product sort of flips it. So this guy commutes, so that's kind of convenient. But there's a way to kind of like put these things all together. So in the 19th century, they came up with something called quaternions, and those are kind of like 3D complex numbers. And these are heavily used if you want to sort of, you have a space probe and you're trying to sort of figure out how the thing is rotating around. It's a convenient way to sort of like have rotations that are not just in the plane, but that go out in 3D. Because complex numbers, basically, you can sort of think of when you multiply by a complex number, basically what you're doing is you're rotating something. And so we're going to be talking about all these things that sort of rotate around, and so we're going to multiply by complex numbers a lot. So you can sort of think of a complex number multiplication as basically a rotation, because it just rotates you just end up with this angle that's the sum of two angles. And so if you start off at whatever angle A was at, multiply it by B, it's just going to add the B angle on to the original vector. Just cause a rotation without changing the length. It won't change the length. So there's these quaternions. That's actually where ijk came from, like for vectors. But there's a cooler thing called geometric algebra. So if you ever want to read about this, geometric algebra, like I said, it was invented in the 19th century, but it's kind of a general, it puts all this together into one kind of glop. Because when I first learned this, which I I learned it a long time ago and then completely forgot it and had to go back. But it's just like, sine and cosine, those are closely related to each other. These must somehow be the same thing somehow, or parts of the same thing. And so if you read about geometric algebra, it kind of like combines dot product and cross product and complex numbers into one kind of more coherent thing. But what I presented here is kind of like the standard way that you'll find in any physics textbook. Okay, so that was dot product, which is kind of like a correlation. It turns vectors, a pair of vectors into a number. And then we had cross product, which basically has the two vectors define a plane and then makes another vector that's perpendicular to those two. And this first one is sort of depends on the cosine between the two vectors. This one depends on the sine between the two vectors. And this cross product here, and that cross product looks more like an area in a way. And then we have complex multiply, which is yet different. And the complex multiply is just like a rotation without changing the vector length. So when you multiply by, so if you multiplied by a complex number with length 1, you'll just get a pure rotation. If you're multiplying by a complex number that doesn't have length 1, well, because the length is just equal to, the length of it is equal to the length of A times the length of B, it's going to change the length. But if complex number B happened to have length 1, then it's convenient. It just causes a pure rotation without any stretching. Okay, so there they were, all together. So now let's finally go back to the, which side should we erase? Yeah, let's erase this side. Okay, before I erase, any last questions about the dot product, cross product, complex multiply? You might have done this or might not have. If you're taking any physics class, you would have done this. If you haven't, that's okay too. It's not a problem. You're not going to be able to remember this the first time, but it just gives you some idea that, like I said, it could be understood. It's just bookkeeping. So now let's talk about how the cross product helps us and why it's in the Bloch equation. So if you look at that cross product, so it's going to involve those, 6 multiplications, but let's just think of it geometrically. I'll just leave this up here, this guy. Think of it geometrically. And so what this says is, how do we calculate the change in the magnetic field vector for a short period of time? We calculate it by taking the cross product between the m vector and the b vector. And so what was the m vector and the b vector again? So So here's the, draw it nice and big. So here's the M vector. So the M vector is whatever the B0 field is at any moment in time, plus whatever you did with the gradients that might have messed up the B0, like say it changed the B0, which is in the Z direction, it slightly changed it as you move in the X direction. That would be the X gradient. And then you might have the RF on as also. It's another magnetic field. You add those all up, and you get one B. So here's our B. So that's whatever the total magnetic field is after we added up all the stuff we've done to it. And then we have another magnetic field. And so that other magnetic field vector is our M vector. And so what is the M vector? The M vector, this guy, was the local magnetization. So this one is, this B vector is, you can sort of think of it as, what is the magnetization if you didn't have anything in there just from the gradients and all the B0 field? This thing is, what does the magnetization do to all those little atomic refrigerator magnets all added up? So it's another magnetic field. So here's the M vector. And so that guy is, we call that the local bulk magnetization. And what's actually causing it? Well, it's those funny atoms that are popped into like sort of 54 degrees this way or 54 degrees this way, and there's a few more of them sort of like lined up, then not aligned up, and then they may or may not be sort of going together with each other. Maybe they're slightly going out of sync with each other. Forget about all that detail, just add them all up and we get one vector. And now the problem is, how does that change? And so the way we calculate it, we just do a cross product. And so what is the cross product? So the cross product is going to be another vector that's perpendicular to both of these guys. So it'll be perpendicular to this guy, but it'll also be perpendicular to this guy. So if you take the B vector and the M vector and make a plane, and then make this resultant cross product vector come out perpendicular to it, that's going to be our dm dt vector. So that's going to be the vector that tells us how to change the M vector. And one thing that I forgot to mention about the cross product, one thing you can see with the cross product, you can immediately see which way does the arrow point? Is it pointing into the board or out of the board? Yeah, it's kind of hard to remember. And so there's another right-hand rule, a different right-hand rule. And the right-hand rule is if you sweep your fingers with your right hand, if you sweep your fingers from vector A to vector B, so if I sweep my fingers from vector A to vector B, like this, it should point in the direction of C. And that right-hand rule, if you sweep your fingers from the direction from B to A, you'll see that it points the opposite, your thumb points the opposite direction. So that's one convenient way to try to remember which the heck way the vector points. So sweep fingers from vector A to vector B, direction of your thumb tells you what direction the cross product is. So that's how you would figure that it's actually sort of sticking out. It's sticking out in this case. Okay, so what does that do? What does that do over time? So let's sort of draw this this kind of like plane here like that. And we'll make this come out. There we go, it sort of comes out of the picture at us. The B coming out at us. Okay, so the way that we operate this differential equation, or the way that we would solve it, is we would figure out, okay, if we take this change in the m vector and paste it on here, so let's paste that on here. So, make this guy go up there. Then, sorry, I was going to dot the other ones. Let me get that out of there. So if we take that guy and put it in red, and put this guy up here, what is that going to do? That will tell us that in the next time point, this is where the m vector is going to be. So the m vector, a short amount of time later, the m vector is going to be pointing in this direction. But that doesn't tell us, what's going to happen for a large amount of time. And so let's just sort of try to intuit, what's going to happen here. So if that's the next position of the vector, so it went around the circle a little bit, what is that going to mean for the next cross product? So what's going to happen is the plane defined by those two, the original vectors, the b and the m vector, before we modified it, is going to be rotated a little bit because we pulled that that new m vector. So this is m vector new. So we sort of pulled it around the circle a little bit. And so it's going to change the plane. So the next time you calculate the cross product for the next little bit of time, what's going to happen is the cross product will rotate a little bit. The cross product will rotate a little bit because the plane between B and M rotated a little bit. And so it won't rotate much, just a little bit. And so what's that going to do over time? So if we solve this equation, this differential equation, we solve it, what you end up with, it just goes around and around and around. So that is basically precession. So this is, this is precession. And if nothing happens else, like nothing happens with these other terms here, so that there's other terms, plus other terms which we've thrown away. But if we just ignore those other terms, other two terms, then what's going to happen is it will just go around and around and won't change. Now, let's sort of dig down a little bit, and why doesn't it change? Like, why doesn't the length of the vector change? And one reason it doesn't is because we're moving it in a direction perpendicular to the m vector, because remember, we're perpendicular to the m vector, and so that by definition the cross product is perpendicular to both of the vectors. And so if we move it in a direction perpendicular to the vector, it won't change its length. It also won't change the angle between the two vectors. And so let's just sort of write that out. So it doesn't. So update doesn't change length. Of the m vector, and it also doesn't change the angle. Doesn't change the angle either. Similar argument. So it doesn't change this angle between them. And if you do the actual differential equation solution, you'll see that that's what you get. You get something that just continues to precess around, and if there's nothing else getting in the way, it'll just keep going. And if there's no friction, and that's the same exact equation that you have for a top, for a mechanical top. So a mechanical top that's spinning around its axis, And what happens if you've got some gravity on the top, it will start to precess around. If it's just out in space, it'll just sort of spin. But if it's where there's not much gravity out in space, it'll just continue to spin. But if you've got it at some angle relative to the gravity, 54.4 degrees, for example, what'll happen is it'll just precess around and continue to precess around. It won't change its angle relative to the gravity or to the B0 field, to the B field, and it won't change its length. It just keeps going around. So that's the equation. So this is the equation that basically explains the precession. And in this case, we were left, for now. So we left B0 constant. B0 isn't constant, right? So we left it constant. It's not constant because maybe we turned on the RF, and then the RF was changing. Oh, you can see, oh no, everything's now, all bets are off. There's not just precession happening. We're also sort of changing the direction of the B. That could sort of like cause all different sorts of trouble. But we just did this simple case where we left the B constant. And if we left the B constant and we don't have any other things messing with the B, then we're going to get precession. And so this is the first part of the Bloch equation explains why these little proton magnets precess around. And that's what's generating our signal. Okay, so everybody okay with sort of college physics, intro college physics? Because this is the same thing you would do if you were just describing what happens with the top. You can, if you just happen to have a bicycle wheel around, you want to feel M cross B. Just spin up a bicycle wheel. Spin up, that's, spin, same spin. And then if you spin up a bicycle wheel and put it on the ground, slightly off angle, you'll see it'll immediately start to precess around. Same equations. Of course, there's friction, so eventually it'll sort of slow down and hit the ground, but it's exactly the same mechanical kind of thing that's happening with a spinning top sitting in a gravitational field. Except it's with magnetic fields instead, but it's the same equation. Okay, so any questions out there? Just utter shock. It's all just a few numbers, 10, 20 numbers, something like that. Not too many. It's good to keep an I like to sort of present all of them at the same time, complex multiply, dot product, cross product, so you see that they're all slightly tweakedly different. Okay. So this is as bad as it gets. I say that every lecture. It doesn't get any worse than this. Okay, so any last questions about dot product, cross product, complex multiply? Using the cross product to sort of tell us how to update the bulk magnetization vector, and what's the result? It just continuously precesses around, doesn't change its length, doesn't change its angle, just keeps going around. Okay, going. So go back over the videos, just make sure you hit that refresh button. That'll make it work, hopefully. And if anybody has trouble with it still not working, email me and we'll find a way to fix it.